Hi, my name is Lisa Lorenzo, and this is my Physics 2211 Lab 4 about oscillations. So, for the introduction, the overall purpose of today's lab is to use fundamental physics principles and a code simulation in order to 1. Observe and analyze the motion of a spring mass system that has a mass oscillating on a spring while swinging in an arc. And 2. We want to compare the predicted observed motions. And then lastly, we are going to plot the computed energy changes on a graph. So for some of the fundamental physics principles that we're looking at today, the first one we'll be looking at is Newton's second law, which we've seen in all the previous labs, and seen by the formula, and we'll also be using the derived formulas of the position update formula and the velocity update formula. And for the second one is a new one, the energy principle, and this will be the main principle we're looking at today's lab, and it can be given by the given equation. In this one, the change in energy of the system is equal to the work done by the surroundings and the thermal energy exchange with surroundings, which is given by the variable Q. So an overall preview of what we'll be doing first is the video analysis using the tracker software to find the initial conditions, and then 2 will be coding through GlowScript to compare the predicted versus observed, and then we're going to find the energy changes from the GlowScript onto a graph. So for some of the tracker observations, first we'll note is that the system is the mass, earth, and spring, and surroundings is nothing. To find t, we're going to be using the formula given to find the period of oscillation, which is 2 pi square root times m over k. And then I also found vector L using the position L0, and the mass was given at 0.402 kilograms. And the spring stiffness was found to be 6.83. So for the GlowScript code, one of the first changes I did was updating the initial conditions from tracker, and this is from the previous slide from the data from tracker. This includes the mass, the position, and the velocity. One of the next changes I did was updating the constants of G, K, and L0. That's gravity, the spring constant, and then the relaxed length of the spring. And then another change was updating the formulas for length and the energies, and updating the velocity using the momentum principle, as you can see at the bottom. And then lastly, one of the changes made was updating the energy changes formulas for K, U, G, U, S, and E, and those are kinetic, gravitational potential, spring potential, and total energy. So these are the resulting graphs outputted from GlowScript and using the tracker data. In the graph to the right, you can see that blue is the change in kinetic, red is the change in potential gravitational, green is the change in spring potential, and orange is the change in total energy. And as a note, you can see that the change in energy is constant 0, which is the orange line. And for the position versus time graphs to the left, you can see that blue is the model and red is the experimental. So for analysis in the graphs align relatively well for position versus time. There's not many big differences that we can make a comment about. But for some possible sources of error that could have caused some deviation, we could have accounted for more forces to make it more accurate. For example, drag in the original video, motion with the spring mass system. There's going to be other forces that we didn't fully account for. Another source of error is user inconsistency in using tracker, since each of the points at each frame were found manually and they may not have been entirely accurate or consistent. So this may have also caused some deviation. So for the first question, for your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. So yes, it is satisfied as the total change in energy is 0, so the energy was conserved, and this makes sense, it's an isolated system, so the energy should stay the same. And as seen by the graph to the left, you can see that this is true because all the forces totaled to 0, and they equal the orange line, which was constant and at 0 for the entire duration of the experiment. So for the last question, using the data you obtain in tracker, make 2 separate estimates of oscillation periods. First, for estimating period of oscillation from the x position, and second, for estimating the period of oscillation from the y position. So to find the period of oscillation, I averaged 3 full cycles data, and I used the same formula as before for t. And the result of this was an x position average of about 1.7 seconds and a y position average oscillation about 1.61 seconds. And these two estimates vary by about 0.9 seconds, and these differences mean that you will have different spring constants, and it will also result in different graphs. So the data will be different if you change how you find the period of oscillation. And that's it for today's lab. Thank you for watching, and hope you enjoyed.